Welcome to another deep dive. We're taking on designing data-intensive applications.
By Martin Kleppmann.
Yeah. We're going to try to break down each chapter.
Really unpack all those juicy concepts.
And give you some, concrete examples along the way.
So you can really wrap your head around these systems.
Exactly.
It's a pretty fascinating look at the evolution of data systems.
For sure.
We're going to be starting right from the foundations.
Yeah.
And then work our way up to some pretty mind-bending stuff.
I'm excited. So, Kleppmann starts off talking about these three pillars of data-intensive applications.
Right.
Reliability, scalability,
Maintainability.
Can you break those down for us?
Sure. Let's start with reliability. You can
Okay.
think of reliability like building a system that can weather any storm.
Okay.
It's all about minimizing downtime,
Yeah.
making sure that your data is accurate,
Yeah.
even when things go wrong. A
No.
good example of this is like a bank. Their systems need to be incredibly reliable to make sure that account balances are always correct.
That makes sense. Nobody wants their money to disappear because of a glitch.
Exactly.
What about scalability?
So scalability is all about handling growth without, breaking a sweat.
Okay.
Think of platforms like Twitter or Facebook
Right.
dealing with billions of users and posts and all this data.
It's a lot.
So their systems have to be able to handle that massive scale.
Right.
It's like building a house that can just, seamlessly add new rooms.
As your family grows.
Exactly.
Love that analogy.
Yeah.
Okay, so we've got reliability to keep things running smoothly.
Yes.
Scalability to handle the big leagues.
Yep.
What about maintainability? Why is that so important?
Well, maintainability is kind of like good housekeeping for your data systems.
Okay.
It's about making sure that your system is easy to understand,
Yeah.
easy to modify,
Right.
and can be adapted over time as things change. You don't want to end up with one of those legacy systems
Right.
that are just a nightmare to work with.
Yeah, like a tangled mess of code.
Exactly. Nobody wants that.
Okay, so Kleppmann also dives into the world of data models
Yeah,
and query languages.
he does.
He specifically contrasts the relational model, which is like behind SQL databases,
Right?
with the document model,
Yes.
more common in NoSQL databases.
Uh-huh.
Can you walk us through those differences?
Absolutely. So the relational model is all about structure.
Yeah.
Your data is organized into tables
Yeah.
with columns and rows.
Like a giant spreadsheet.
Yeah, exactly, like a giant spreadsheet.
Okay.
And this structure is really great for enforcing data integrity
Right.
and performing complex queries thanks to the power of SQL.
Okay.
A good example is an e-commerce platform.
Okay.
Managing products, orders, customer information.
And it all fits in there nicely.
It fits perfectly there.
Now, what about the document model?
So the document model is all about flexibility. Data is stored in these more free-form documents,
Right.
often in a JSON-like structure.
Gotcha.
This approach is great for applications with, less structured data,
Right.
like content management systems or user profiles,
Okay.
where you might have varying attributes for different things.
So like on a social media platform where every user could have a unique set of interests.
Exactly. That's a perfect example.
Okay, so how do you choose which model's right for your project?
Well, it really comes down to the nature of your data
Yep.
and the queries that you need to perform.
Gotcha.
If you've got a clear structure with relationships between entities, a relational database is usually a good fit.
Okay.
But if you need more flexibility and your queries are less about joins and more about retrieving entire documents,
Right.
then a document database might be the way to go.
So it's not just about picking the cool new technology.
Because it's not.
It's about understanding the strengths and weaknesses.
Exactly. Picking the right tool for the job.
And speaking of different approaches, Kleppmann spends a good chunk of the book talking about storage engines,
Yeah.
which are kind of like the hidden heroes of the database world.
Absolutely.
Can you demystify those for us a little bit?
Sure. So storage engines determine how data is physically written to disk and read back into memory.
Okay.
They're really the foundation of the database.
Right.
They play a huge role in performance,
Yeah.
reliability,
Yeah.
and the types of queries that a database can handle efficiently.
Yeah.
It's like choosing the right type of engine for a car,
Yeah.
A sports car needs a different engine than a truck hauling heavy loads.
Makes sense. So different engines for different jobs.
Exactly.
Can you give us some concrete examples?
Sure, let's take log-structured storage engines.
Okay.
These are kind of like high-speed scribes constantly writing new data to a log.
Okay.
They're really great for write-heavy workloads, like capturing a stream of sensor data.
Okay, so like constantly adding information.
Exactly.
Okay, cool. Then you have page-oriented storage engines,
Right.
which are more like organized librarians,
Yes.
carefully arranging data into these pages. These are good for transactional systems.
Yeah.
Where you need to read and update data quickly.
Exactly.
It's like a more traditional database setup.
Yeah, you could say that.
It's fascinating how these different structures optimize for different use cases.
It is, isn't it?
But how does a database actually find the data it needs?
Oh, that's a great question.
Like among gigabytes or even terabytes of information.
Right.
It's got to be more than just a brute force search, right?
It is. That's where indexing comes in.
Okay.
An index is like a super efficient lookup table that really speeds up data retrieval.
Gotcha.
It's like adding a detailed table of contents to a massive book.
Right.
So you can jump directly to the information you need.
Without flipping through every page.
Exactly.
Okay, so indexing is all about making searches faster.
Yeah.
What are some common indexing techniques?
So there's a whole toolbox of techniques out there,
Oh, yeah?
each suited for different scenarios.
Right.
You've got hash indexes, for instance.
Okay.
They're really simple and blazing fast for exact key value lookups.
Okay.
Think of a cache storing frequently accessed web pages.
Okay.
A hash index can quickly retrieve the page associated with a given URL.
Gotcha.
Then you have B trees.
Okay.
They're more sophisticated, and they excel at range queries.
Okay.
Imagine you're searching for products on an e-commerce site within a certain price range.
Right.
A B-tree index can efficiently find all the products that match those criteria.
So hash indexes are like a phone book, and B trees are like a well-organized library catalog.
That's a great way to put it.
It's all about choosing the right tool for the job.
Absolutely.
Now, Kleppmann also talks about data encoding.
He does.
I know this is a crucial aspect of data systems.
It is.
But it can feel a bit abstract sometimes.
Yeah.
Can you make it more concrete for us?
Sure. Think of data encoding as translating information into a format that computers can understand and work with.
Right.
It's like choosing the right language for a conversation, right?
Okay.
You wouldn't use technical jargon when talking to a child.
Right.
And you wouldn't use emojis in a formal business document.
Makes sense. So it's about picking the right format for the context.
Exactly.
What are some common encoding formats?
Well, you've got language-specific formats like Java serialization or Python's pickle, which are really convenient for working within a single programming language.
Okay.
It's kind of like using shorthand within your team, but it might not be understood by people outside of that team.
Gotcha.
Then you have more standardized formats like JSON and XML,
Yeah.
which are human-readable
Right.
and widely used for exchanging data between systems.
They're like the universal languages of the internet.
That's a good way to put it.
But are there any downsides to using these human-readable formats?
Oh, yeah.
Yeah.
While they're great for readability and debugging,
Right.
they can be less efficient.
In terms of those.
Storage and processing.
Gotcha.
It's like writing a message in full sentences versus using abbreviations.
Okay.
The full sentence is easier to understand,
Yeah.
but the abbreviation is much shorter
Right.
and quicker to transmit.
Ah, so there's a trade-off.
Exact.
Readability versus efficiency.
That's right.
What are some of the more efficient encoding formats?
So for efficiency, you have binary formats like protocol buffers and Avro.
Okay.
They're more compact,
Yeah.
faster to process,
Right.
but
Right.
they're not human readable.
Okay.
And they require schema definitions.
So it's like speaking in code.
Yeah, it's efficient.
But only understood by those who know the code.
Right, right. So it's another example of choosing the right tool for the job.
Absolutely.
You wouldn't use Morse code to chat with your friends,
Probably not.
but it might be the best option for, a long-distance transmission with limited bandwidth.
Now, one of the biggest challenges that Kleppmann addresses is the inherent complexity of distributed systems.
Right.
It's like going from a single-player game to a massive online multiplayer world.
It is.
What are some of the key challenges of working with these distributed beasts?
Well, one of the biggest hurdles is the fact that networks aren't perfectly reliable.
Right.
You have to deal with network partitions.
Okay.
Where parts of the system become isolated from each other.
Like islands suddenly appearing in the middle of the ocean?
That's a great analogy.
I try.
Yeah.
And then you have unreliable clocks.
Right.
Where different machines have slightly different notions of time.
Yeah.
Which can lead to inconsistencies.
It can.
It's like trying to coordinate a dance routine where everyone's metronome is slightly off.
Yeah, that's a good one.
Thanks. It sounds like a recipe for chaos.
It can be.
How do you even begin to design systems that can handle all of this uncertainty?
Well, the first step is acknowledging that these things will happen. We can't just pretend that networks and machines are perfect.
Right.
Once we accept that reality,
Yeah.
we can start to design systems that are fault tolerant
Okay.
and can gracefully recover from errors.
So it's about anticipating failure and building in safeguards.
Exactly.
What are some specific techniques for building fault-tolerant distributed systems?
So Kleppmann discusses a variety of techniques,
Okay.
including replication, where data is copied across multiple machines,
Okay.
and partitioning,
Yeah.
where data is divided into smaller chunks and distributed across the system.
Gotcha.
He also emphasizes the importance of using consensus algorithms
Okay.
to ensure that all nodes agree on the state of the system,
Even in the face of failures.
even in the face of failures.
It sounds like a delicate balancing act,
It is.
ensuring that data is consistent, available,
Yeah.
resilient to all sorts of potential disruptions. It's like a complex choreography of data, constantly moving and adapting
That's a beautiful way to put it.
to maintain harmony across the system.
I like it.
I'm a poet, and I didn't know it.
There you go.
All right, well, that's a great start to our deep dive
Yeah,
into designing data-intensive applications.
it is.
We're just scratching the surface here, folks.
We are.
There's so much more to explore.
There is.
We'll be back soon
That's good.
to dive even deeper into these fascinating concepts.
I'm looking forward to it.
Me too.
All right.
Thanks for joining us.
See you next time. Welcome back to the deep dive.
All right, so last time we talked about the fundamental challenges of building these, reliable, scalable, maintainable, data-intensive applications.
Absolutely.
We explored data models, storage engines, indexing techniques,
All that good stuff.
the wild world of distributed systems.
It's a jungle out there.
It is. It is.
Yeah.
And today we're going to kind of build on those foundations
Huh?
and explore how we can actually process and derive insights from
Yes.
the massive amounts of data that these systems handle. So Kleppmann takes us on this journey through different approaches to data processing.
He does.
And he starts with batch processing, which is kind of like the workhorse
Yeah,
of data analysis.
it is.
But batch processing, it sounds kind of old school.
I know, right?
Like something you do with punch cards and mainframes.
Yeah,
Is it still relevant in today's world of real-time data?
absolutely. Batch processing is all about processing large volumes of data in one go,
Okay.
typically offline.
Right.
Think of it like baking a giant cake. You
Okay.
gather all the ingredients, mix them according to the recipe,
Uh-huh.
and then you bake it all at once.
Okay, I'm getting hungry already.
Yeah.
But how does this cake analogy actually apply to data processing?
So imagine you have a massive data set
Okay.
stored in a distributed file system like HDFS.
Right.
A batch processing framework like MapReduce allows you to define a series of steps,
Okay.
a map step and a reduce step,
Right.
to process this data in parallel across multiple machines.
So it's like having a team of bakers working together to create this giant multi-layered cake.
Exactly.
Can you break down those steps a little bit more for us?
Sure.
What exactly happens during the map and reduce phases?
So in the map step,
Yeah.
each worker node processes a portion of the data
Okay.
and emits these key value pairs
Right.
based on some logic that you define.
Okay.
It's like each baker preparing their assigned layers of the cake.
Gotcha.
These pairs are then shuffled across the network,
Okay.
grouping together all the values with the same key.
Right.
This is like arranging all the cake layers together based on their type.
Okay, like chocolate, vanilla, red velvet, and so on.
Exactly.
Okay.
Then, in the reduce step,
Yeah.
each worker node processes these grouped values
Okay.
and produces the final output.
Gotcha.
This is like assembling and frosting the entire cake.
Creating a delicious masterpiece.
Exactly.
So it's a divide and conquer approach to data processing. What are some real-world examples where batch processing really shines?
Oh, there are countless applications.
Okay.
Think of building search indexes for a massive website,
Okay.
generating personalized recommendations
Yeah.
based on user behavior, analyzing financial data to detect trends, or processing scientific data to make new discoveries.
Right.
Any task that involves crunching through large amounts of data
Yeah.
can benefit from batch processing.
So MapReduce was a real game changer for batch processing.
It was.
But is it still the go-to framework today?
Well, MapReduce was revolutionary, but the data landscape is constantly evolving.
Sure.
Today, we have these more modern data flow engines,
Okay.
like Apache Spark and Apache Flink,
Right.
which offer more flexibility, better performance, and a wider range of features.
So they're like having a team of master pastry chefs
Exactly.
who can create even more elaborate and delicious cakes.
That's a great analogy.
What makes these modern engines different from MapReduce?
Well, one key difference is that data flow engines focus on pipeline execution,
Okay.
where data is processed incrementally as it flows through a series of operators.
So it's like having a conveyor belt in a bakery,
Yeah.
where each step in the cake-making process happens seamlessly
Exactly.
as the cake moves along the line.
That's right.
Okay, so it's like a continuous flow of data
Yeah.
rather than discrete batches.
Exactly.
That sounds much more efficient.
It often is.
Now, Kleppmann also mentions graph processing as a specialized form of batch processing.
Yeah.
When would you choose to use a graph processing approach?
Well, graph processing is perfect for analyzing relationships between entities.
Okay.
Think of social networks, recommendation engines,
Right.
fraud detection systems,
Right.
even analyzing the spread of a virus.
Right.
These all involve graphs of interconnected data points.
Okay.
And graph processing allows you to understand the connections and patterns within those networks.
So it's like mapping the constellations of relationships
It is.
within a data set.
Yeah, that's a great way to put it.
What are some common graph processing frameworks?
So there are frameworks like Apache Geograph and Google's Pregel,
Okay.
which are based on this think like a vertex paradigm.
Okay.
These frameworks allow you to define algorithms that operate on individual nodes in a graph,
Okay.
iteratively propagating information across the network of connections.
So it's like sending messages along the edges of a graph,
Exactly.
allowing information to flow and insights to emerge.
That's right.
This is mind-blowing. We've gone from baking cakes to mapping constellations.
It's quite a journey.
It is. Now, let's shift gears a little bit. Talk
Okay.
about stream processing.
Sure.
This feels like the real frontier of data processing,
It does.
where we're dealing with this constant influx of information
Right.
in real time.
Yeah.
Stream processing is all about dealing with these unbounded streams of data
Yes.
that arrive continuously.
That's right.
Think of real-time analytics, dashboards,
Yeah.
fraud detection systems that need to flag suspicious transactions immediately.
Right.
Monitoring sensor data from a fleet of self-driving cars.
Perfect examples.
These all require processing data as it arrives, not in batches.
That's right.
So it's like trying to drink from a fire hose of data.
Yeah, it can feel like that.
How do stream processing systems handle this constant influx of information?
Well, they use a combination of buffering,
Okay.
windowing, and aggregation techniques
Okay.
to process the data in real time.
Right.
So messages are typically buffered as they arrive,
Okay.
grouped into these time-based or count-based windows, and then processed within those windows.
So it's like having a series of buckets
Yeah.
that collect the incoming water from the fire hose,
Exactly.
allowing you to process it in manageable chunks.
That's a great analogy.
Okay, so we're slicing the data stream into manageable portions
Yes,
and processing them on the fly.
that's right.
What are some common stream processing frameworks?
So we have Apache Kafka, which is this high-throughput distributed messaging system
Right.
often used as the backbone for these stream processing pipelines.
Okay.
It's like the plumbing that carries the data stream.
Gotcha.
Then you have frameworks like Apache Storm,
Yeah.
Apache Flink, Apache Spark Streaming,
Right.
which provide tools for defining and executing these stream processing jobs.
So Kafka handles the data flow.
Yeah,
These other frameworks provide the processing logic.
that's right.
Now, traditionally, databases and streams have been seen as separate domains.
They have.
But Kleppmann talks about this convergence of these technologies.
He does.
What's driving this convergence?
I think one key driver is the need for real-time insights.
Okay.
We no longer want to wait for batch jobs to complete to
Right.
understand what's happening in our systems.
We want to see changes as they occur.
Exactly. And react accordingly.
Okay.
This has led to techniques like change data capture,
Okay.
where changes to a database are captured as a stream of events.
So it's like having a live feed of all the modifications
Yeah.
happening in the database.
That's right.
So it's like treating the database itself as a source of events
It is.
that can trigger actions in other systems.
Absolutely.
This opens up a whole world of possibilities for integrating databases and streams
Does.
into this unified data architecture.
Yeah.
We can have real-time dashboards
Yep.
that reflect the latest database updates, trigger alerts
Right.
based on specific data changes, or even feed database changes into machine learning models. for real-time predictions.
Exactly.
This is amazing. We're breaking down the silos between databases and streams.
We are.
Creating systems that are more responsive and insightful.
That's right.
Kleppmann also introduces this concept of unbundling databases.
Yeah, he does.
What's that all about?
So unbundling databases is a trend towards composing systems from specialized components, rather than relying on these monolithic databases.
Gotcha.
It's like building a custom stereo system. With individual components, you pick the best amplifier, speakers, turntable for your needs, rather than just buying a prepackaged system.
So it's about choosing the best tool for each job.
Exactly.
Rather than trying to force one database to do everything.
That's right.
Okay, so we might use a separate database for storing user profiles. Another one for handling transactions. Yet another for full text search.
Right.
But the key is to integrate these components into a cohesive system.
Yes.
Using data flow mechanisms like batch and stream processing.
Exactly.
That sounds incredibly flexible.
Yeah.
But also potentially complex.
It can be, yeah.
How do you manage the complexity of an unbundled database architecture?
Well, that's the challenge.
Okay.
We need to carefully consider data flow, consistency, and fault tolerance when we're integrating these multiple components.
Yeah.
But the rewards can be significant.
Okay.
Greater flexibility, scalability, the ability to choose the best technology for each specific need.
So it's like assembling a team of specialists.
Yeah.
Rather than relying on a single generalist.
That's a good way to put it.
Now, we've covered a lot of ground in terms of data processing techniques.
We have.
But Kleppmann doesn't just focus on the technical aspects.
No, he doesn't.
He also delves into the broader implications of data systems.
Right.
Particularly the ethical considerations.
He does.
Can you elaborate on that a little bit?
Sure. As data systems become more pervasive and powerful, it's really crucial to consider the ethical implications of how we collect, store, and use data. We need to think about privacy, bias, and the potential for harm.
It's like the Spider-Man quote. With great power comes great responsibility.
Exactly.
What are some key ethical considerations when designing these systems?
We need to be transparent about how we collect and use data. Obtain informed consent from users. And protect sensitive information from unauthorized access. We also need to be aware of potential biases in our data and algorithms and really strive to build systems that are fair and equitable.
So it's not just about building systems that work.
No.
It's about building systems that are ethical and responsible.
Exactly.
All right, well, I think that's a great place to pause for now. We'll continue this conversation in our next segment.
That's good.
Welcome back to the Deep Dive. We've been exploring designing data-intensive applications.
It's been a fascinating journey.
It really has. And in this final part, we're going to shift our focus from those technical nuts and bolts to the bigger picture.
The grand scheme of things.
Yeah. The future of data systems and the responsibility that comes with building these powerful tools.
Absolutely. It's an important conversation to have.
It is.
Especially as data systems become, more and more integrated into our lives. We need to think beyond just efficiency and performance.
Beyond the technical.
Exactly.
Really consider
the ethical implications and the long-term impact on society.
Absolutely. And one of the key themes that Kleppmann emphasizes is this idea of correctness in data systems. And it's not just about, preventing crashes or data loss. It's about building systems that behave as expected. Even in the face of unexpected events.
That's right.
Why is this concept of correctness so challenging in the world of distributed systems?
Well, distributed systems introduce a whole new level of complexity when it comes to correctness. We have to deal with concurrency, network failures, the possibility of nodes crashing or behaving unpredictably.
Yeah, all sorts of things can go wrong.
Exactly. So ensuring that data is processed accurately and consistently across a distributed system can feel like trying to herd cats.
I love that analogy.
Yeah.
Especially since those cats are, computers spread across a network, potentially disappearing at any moment.
Exactly.
It's a recipe for disaster.
It can be, yeah.
So it's not just about writing bug-free code.
Right.
It's about designing systems that are resilient to all sorts of potential disruptions.
Absolutely.
So what are some strategies for achieving this level of robustness?
Well, Kleppmann dives into several approaches, including the use of transactions.
Right.
which basically ensure that a series of operations either complete successfully
Yeah.
or they have no effect at all.
So it's like a safety net.
It is.
For data operations.
Exactly. He also discusses idempotency,
Okay.
where an operation can be executed multiple times
Right.
without changing the result.
Right.
And exactly. Once the semantics,
okay,
in-stream processing, which basically ensures that each message in a stream is processed only once. Even if there are failures.
Even with those crazy cats running around.
Exactly.
It sounds like this delicate dance.
It is.
Between ensuring data integrity.
Yeah.
Handling failures gracefully.
Right.
Keeping the system humming along smoothly.
That's a great way to put it.
And I imagine careful testing, monitoring, and auditing.
Absolutely. Those are crucial.
Are crucial to, verify that the system's behaving as expected.
Yeah, it's like having a team of inspectors.
Yeah.
Constantly checking the bridge for any cracks or weaknesses.
Right. You got to make sure it's all solid.
You do.
Now, Kleppmann also talks about this concept of data provenance.
Yeah.
Which is, kind of like tracing the lineage of data.
It is.
Understanding its origin.
Right.
The transformations it underwent.
Yeah.
How does that relate to this broader idea of correctness?
Well, data provenance is crucial for verifying the accuracy and reliability of data.
Okay.
It allows us to trace errors back to their source.
Right.
Understand how data was impacted by different processing steps.
So it's like having this detailed log of every ingredient that went into a dish in every step in the cooking process.
Exactly.
If something tastes off, you can go back and see exactly where things went wrong.
That's right.
It's like having a detective's toolkit for data. It is, yeah. You can retrace the steps, examine the evidence, and ultimately build a stronger case for the reliability of your data.
Absolutely.
Now, as we wrap up this deep dive, I want to touch on one more important aspect that Kleppmann emphasizes.
Okay.
Which is this responsibility that comes with building these data-intensive applications.
Yes.
These systems are incredibly powerful.
They are.
And it's really crucial that we use that power wisely.
Absolutely. We need to be mindful of the potential impact of our work on individuals and society as a whole. Yeah. We have a responsibility to protect privacy, ensure fairness, build systems that are ethical and beneficial.
Data is a powerful tool.
It is.
And like any tool, it can be used for good or for ill.
That's right.
And it's up to us, the builders of these systems, to make sure that we're using this power responsibly, ethically.
Couldn't agree more.
We need to move beyond that purely technical mindset and really consider the human element in everything we do.
Absolutely.
Be transparent, accountable, always striving to build systems that make the world a better place.
Well said.
So for all you data enthusiasts out there, as you embark on your own data adventures, remember, it's not just about building cool technology.
All right.
It's about building a better future.
That's right.
Keep exploring.
Keep learning.
Keep questioning.
Keep building.
Keep striving to use data for good.
Couldn't have said it better myself.
And with that, we'll wrap up this deep dive into designing data-intensive applications.
It's been a pleasure.
It really has. Thanks for joining us, everyone.
See you next time.